Modeling word problems as matrix equations. Welcome, everyone. Today, we are moving beyond the basics of matrix algebra. In our previous lessons, we focused on the mechanical process of solving a system of linear equations. Essentially, you were given the equations and you knew exactly which steps to take using the matrix method. However, in the real world, mathematics doesn't usually present itself as a neat list of equations. Instead, information is often hidden within descriptive text or complex scenarios. To be successful in applied mathematics, you need more than just calculation skills. You need the ability to translate these word problems into a formal mathematical model. In this tutorial, I am going to guide you through a systematic, step-by-step process. We will learn how to extract linear equations from a written word problem and then organize them into the matrix equation, a times x equals b, to find our solution. Let's get started. The step-by-step modeling process. Now that we've established that the real challenge lies in translating descriptive text into mathematical language, let's look at how we can approach this systematically. To solve a word problem using matrices, you don't need to guess. You simply need to follow these 4 logical steps that we are about to break down. Step 1. Identify and define the unknowns. Now that we have our roadmap for the modeling process, let's dive into the very first, and perhaps most crucial, step: identifying and defining our unknowns. Before you even pick up your pen to write an equation, you must read the problem statement very carefully. Your first goal is to pinpoint exactly what the question is asking you to find. Are you looking for prices, weights, or quantities? Once you have identified these unknown quantities, you need to assign a unique variable to each one. We typically use simple letters like x, y, or z to represent these values. This keeps our mathematical model organized. To make this clearer, let's look at a quick example. Suppose a word problem asks you to find the cost of an apple, an orange, and a banana. To start our model, we would explicitly state, let x be the cost of an apple, let y be the cost of an orange, and let z be the cost of a banana. By clearly defining these variables now, you are setting the foundation for the next step, where we will translate the rest of the problem's sentences into algebraic equations. Step 2. Translate sentences into algebraic equations. Now that we have identified our unknowns and assigned them variables, as we saw in the previous step, we need to perform the most crucial part of the modeling process, translating those English sentences into algebraic equations. Think of yourself as a translator, moving from the language of words to the language of mathematics. To do this accurately, you need to keep a sharp eye out for specific mathematical keywords. First, look for words like total or sum. Whenever you encounter these, they are your signal to use addition or the plus sign. Next, pay attention to multipliers. If a problem mentions twice or thrice a certain quantity, this indicates multiplication by 2 or 3, respectively. On the other hand, if you see words like difference or less than, these are your cues to use subtraction or the minus sign. Finally, you need to know where the equation ends. Words like is, equals, or results in are the indicators for the equals sign. By mastering these linguistic cues, you will be able to build the system of equations necessary to move into the next step, where we organize these equations into our matrix form. Step 3. Represent the system in matrix form. Now that you have successfully translated your word problem into algebraic equations, as we discussed in the previous step, you need to organize them properly before we can move into the matrix stage. First, take a close look at your equations and ensure that all your variables are aligned. This means you must arrange them so that, for example, every x is in the first position, every y is in the second, and every z is in the third, across every single equation. Consistency here is vital for the next step. Once they are aligned, we are going to compress that entire system of equations into a single, elegant matrix equation in the form a times x equals b. Let's break down what these 3 components actually represent. First, we have A, which we call the coefficient matrix. This matrix is simply a collection of the numbers that are multiplying your variables, the coefficients. Next, we have X, the variable matrix. This is a single column matrix that holds all your unknowns, like X, Y, and Z, stacked vertically. Finally, we have B, the constant matrix. This is also a column matrix, but instead of variables, it contains the values from the right side of your equals signs, the constants. By structuring your problem this way, we transform a messy set of sentences into a structured mathematical format that we can solve using the systematic steps we will cover in the next slide. Step 4. Solve for the variable matrix. Now that we have successfully organized our equations into the matrix form, we move on to the final stage of our process. On this slide, we will look at how to actually solve for our unknown variables using the matrix method. First, we need to calculate the determinant of matrix A, which we write as the absolute value of A. This is a crucial first step, because it tells us if a solution even exists. Second, if we find that the determinant of A is not equal to 0, we can proceed to find the adjoint of A, which is written as a J. Third, once we have both the determinant and the adjoint, we can compute the inverse of matrix A. We express this as an inverse, which is equal to 1 divided by the determinant of A, multiplied by the adjoint of A. Finally, the last step is to solve for our variable matrix X. We do this by using the formula X equals an inverse multiplied by matrix B. Once you perform this multiplication, the resulting values in matrix X will give you the exact answers to the unknowns we defined at the beginning of our problem. In the next slide, we will put all these steps into practice with a real-world example. Comprehensive example. Now that we have walked through the theoretical steps of identifying unknowns, translating sentences, and setting up the matrix equation, let's put everything we have learned into practice with a comprehensive example. Take a look at this problem. We have 3 friends, Amit, Binny, and Chitra, who all visited a stationery shop, and we have the details of their respective purchases. First, we see that Amit bought 1 notebook, 1 pen, and 1 eraser, and his total bill came to $6. Next, Binny purchased 2 notebooks, 1 pen, and 0 erasers, totaling $7. Finally, Chitra bought 1 notebook, 0 pens, and 1 eraser, for a total of $4. Our objective here is to determine the individual cost of a single notebook, a single pen, and a single eraser. As we move to the next slide, we are going to apply the 4-step process we just discussed to break this word problem down into a solvable matrix equation. Solution breakdown. Now that we have reviewed the problem statement, let's walk through the complete solution step by step, following the systematic process we discussed in the previous slides. Step 1, we begin by defining our variables. As I mentioned in the modeling process, we must assign a unique variable to each unknown. Here, let X represent the cost of 1 notebook, Y represent the cost of 1 pen, and Z represent the cost of 1 eraser. Step 2, next we translate the sentences from the word problem into algebraic equations. Looking at Amit's purchase, 1x plus 1y plus 1z equals 6. For Binny, we have 2x plus 1y plus 0z equals 7. And for Chitra, 1x plus 0y plus 1z equals 4. Notice how we use 0 for the missing items, a point we will revisit later in our discussion on common mistakes. Step 3, now we represent the system in the matrix form. A times x equals b, our coefficient matrix. A is a 3x3 matrix where the first row is 1, 1, 1, the second row is 2, 1, 0, and the third row is 1, 0, 1. Our variable matrix X is a column matrix containing X, Y, and Z. Finally, our constant matrix B is the column matrix containing our totals, 6, 7, and 4. Step 4, now we move to the mechanical process of solving the system. First, we find the determinant of matrix A. We calculate this by taking 1 times the quantity 1 minus 0, minus 1 times the quantity 2 minus 0, plus 1 times the quantity 0 minus 1. This simplifies to 1 minus 2 minus 1, which results in a determinant of negative 2. Because this determinant is not equal to 0, we are certain that a unique solution exists. Next, we find the adjoint of A by calculating the cofactors. For instance, C sub 11 equals 1, C sub 12 equals -2, and so on. We can construct the adjoint matrix. This adjoint matrix A consists of the first row, 1, -1, -1, the second row, -2, 0, 2, and the third row, -1, 1, -1. Finally, we calculate x using the formula x equals A inverse, which is 1 over the determinant, times the adjoint, all multiplied by matrix B. When we multiply the adjoint matrix by our constant matrix B, we perform the dot product for each row. This gives us a new column where the first element is 6 minus 7 minus 4, which is -5. The second is -12 plus 0 plus 8, which is -4, and the third is -6 plus 7 minus 4, which is -3. We then multiply this entire column by 1 over -2. This results in our final values for x equals 2.5, y equals 2, and z equals 1.5. To conclude, we have our final answer. The cost of a notebook is $2.50, the cost of a pen is $2, and the cost of an eraser is $1.50. As we move to the next slide, pay close attention to the calculation steps, as these are areas where errors often occur. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the theory, these small errors can lead to incorrect results. First, watch out for incorrect variable alignment. I've seen many students write equations where the variables are in different orders. For example, writing x plus y equals 5 in one line, but then switching it to y plus x equals 6 in the next. This is a major error. You must ensure that every column in your coefficient matrix corresponds strictly to the same variable, in the exact same order, across every single equation. Second, do not ignore zero coefficients. This is a very important point, especially looking at our example with Binny's purchase. If a variable is missing from an equation, like the eraser in Binny's case, you cannot simply skip that column. You must explicitly use a 0 as the coefficient in matrix A. If you leave it blank or skip the column, your matrix dimensions won't match, and the multiplication will become impossible. Third, be extremely careful with sign errors during your adjoint calculation. This is perhaps the most frequent mistake I see. When you are calculating cofactors, you must remember to apply the alternating sign pattern, which starts with a plus, then a minus, then a plus, and continues in a checkerboard fashion: plus, minus, plus, minus, plus, minus, and finally plus, minus, plus. Forgetting to flip that sign can ruin your entire inverse matrix. Finally, make sure you aren't confusing matrix B with matrix X. Always double-check that your constant terms, the totals from the word problem, are placed strictly in the B matrix, and ensure they haven't accidentally been mixed into your coefficient matrix. Keep these in mind, and you'll find much more success with these complex problems. Key takeaways. To wrap up our session today, let's review the key takeaways from this tutorial to ensure you have a solid foundation for solving these types of problems. First and foremost, remember that translation is key. As we saw when we moved from the word problem about the stationery shop to our algebraic equations, the most critical step in modeling is accurately converting English sentences into linear equations. If your initial translation is incorrect, the rest of your matrix calculations will be based on a flawed model. Second, always aim for standard form. Before you even think about constructing your matrices, make sure you have arranged your equations so that the variables are in the same order in every line, specifically in the form of a coefficient times x, plus a coefficient times y, plus a coefficient times z, equals a constant. This prevents the alignment errors we discussed in our common mistakes slide. Third, keep the matrix equation structure at the front of your mind. The relationship between your coefficients, your unknowns, and your totals is always represented as a times x equals b, and as we practiced in our step-by-step solution, you find the values for your variables by calculating the inverse of A, which we write as a inverse, and then multiplying it by b. Finally, never skip the verification step. Once you have calculated your final values for x, y, and z, plug them back into the original descriptions of the problem. For instance, check if the costs we found for the notebook, pen, and eraser actually add up to the totals paid by Amit, Binny, and Chitra. If the totals match, you can be completely confident in your solution. Well done today. Keep practicing this systematic approach, and you'll master mathematical modeling in no time.